Hello, everyone. So welcome to this new module of hashing. In this module, first we are going to look at what is the motivation behind hashing. Now, hashing is one of the most popularly used data structure in computer science. So let's first begin with why is it so? We are going to look at some of the application of where hashing is used, and that would motivate the hashing concept itself. Then to begin with the concept of hashing, first we are going to look at one of the simplest approach of how can we perform hashing. Then we will see the drawbacks of this simple approach. So what is the problem with this simple approach? Then we'll try to address that problems that exist with simple approach and design our more advanced new hashing methods. So discuss those. Finally, while discussing how are we solving the some of the major drawbacks, we will look into collision that we will soon define when we are discussing hashing in more detail. And at the end, we will look at some of the hashing, popularly used hash functions. So hash function is at the center of hashing concept. So we'll look into some of the hash functions and how can we design them and how do we kind of come up with a good hash function. So we will just look at some of the examples of designing hash functions. So let's begin. Let me share my tablet screen. Okay, so you should be able to see my iPad. Okay, so hashing is one of the most commonly used data structure in computer science. And I believe most of you over here in this class would have definitely heard of hash tables, hashing, dictionary. It goes with different names in different language. In C++, we call them hash tables, and Python, we call them dictionaries. But most of you here would have heard of these things, even if you don't know more about that. So it's something popular. Why is it so popular? So what's the motivation behind hashing? One of the best thing that hashing brings to the table of data structures is hashing allows you to query any data at the cost of big O of 1. And this is why it is such a popular data structure. So if you have a blob of or different items stored in this data structure, if you want to know if any particular item exists here or not, you can just look into this blob of data. If this data is using hash data using the hash functionalities, so if it's C++, if it's using the hash table, then you can perform this query just with a constant cost big O of 1 in worst case. Now, if you just recall what was the cost of some of the data structures that we used previously to query. Let's say, for example, if you are using list, then in list, if you want to find any particular item, then you have to go right from the head of the list until the tail, looking one by one, searching for that item, doing next, 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 right? Item dot next, and that's how you will keep on searching if you find the item that you're looking for or not. So if the size of the list is n, the cost of query was big O of n. If it's an unsorted array, and if you don't know the index of the item that you're looking for, if you know the index, that's just big O of 1, because if it's an array A, you can look into something like A of 5, and that's just a constant cost. But let's say for the item that you are looking for, the item that you're searching, let's say you're searching for integer 59, and you don't know what's the index of this integer 59 in that array, Then if it's an unsorted array, again, you have to go from the beginning of the array of 0 until the length of the array and keep on searching. Is this item 59? Is this the next item 59? So you have to go through the whole size of data. That's again big O of n. If it's a sorted array, then you have bit smarter algorithm, which is an algorithm you can use to search item in a sorted array. Binary search, if that's the one that's on your mind, you are perfectly correct. So if it's a sorted array, then we can take advantage of advanced algorithm like binary search. And using binary search, you can find any item at the cost of big O of log n, because then you have to just search half and then half. So the cost of doing binary search on a sorted array is big O of log n. If it's a binary search, if the data structure is binary search tree, then as we saw in our last module, what's the cost of finding an item in a binary search tree? This should be very recent. I think most of you should have this like on the tip of your tongue, ready to spell out, right? The cost of doing search in a binary search tree is nothing but big O of h, where h is the height of the tree. So on and so forth. As you see, searching an item in a data structure is something that has a big application, right? If you have like lots and lots of data, but if you don't know what's there in that data, then what's the point? So searching is one of the operation that whenever you have like group of information, searching is one of the obvious operation that you would want to perform given any different application. And this operation of searching does cost pretty expensively depending on which data structure are we using. And that's the whole purpose of hashing, which allows us to perform this search at this constant cost. Definitely, big O of 1 looks like way better than all this, right? And that's the reason why this data structure is that popularly used. Now, understanding the motivation behind why this data structure is that popular, what are the application of this data structure? Can somebody name some of the application where hashing is used? Depending on your profession or depending upon some of the previous courses that you took, previous work you are involved with, you might have come up with something like, if you are from computer systems background, then you could come up with something like caching is where we use hashing the most. Caching is nothing but you want to save the information that your CPU in a computer system, you want to save the information that your CPU is using more frequently, very near to the CPU, so that whenever this information is required, it's quickly accessible. Then rather than storing it far, which would take more time to access that information. So that's caching, and hashing is used, like there are many algorithms to do caching that uses hashing or hash table as a data structure. We have some another applications like, let's say, for example, if you want to compare words in different documents. So you have a couple of documents where you want to see that if this word exists in all those documents, or how many times is this word used in each of these documents, what is the most commonly used word among all those documents. So all these type of queries. Hashing is popularly used in such type of applications where you want to find such answers to such questions. And related to that, we can say that hashing is used popularly in database. There are many databases that uses hash table as its key data structure within the database. So hashing is popularly used in different databases. Hashing is definitely used in compilers and interpreters. Now that we have many high-level languages like C++, Java, Python, most of you might not be aware of compiler level language. But if you ever had to deal with compiler level language, then hash tables also have applicability in designing of our compilers. Hashing is used in what else? Let's say virtual memory. Yes, virtual memory is one of the biggest application of hashing. If you are aware of, or if you have installed on your laptop multiple operating systems using virtual machines do use concept of virtualization, and most of our modern day system uses virtual memory. So virtual memory in its core at its core uses hashing. Definitely hashing has a popularly used application in cryptography. I should make my eraser smaller. Well, a year back or 2 years back, right? There was like this boom of um everybody knowing Bitcoin and everybody knowing the cryptocurrency. So cryptocurrency has a big is a part of cryptographic functions. It does use cryptocurrency. Cryptocurrency uses cryptographic functions, and they're like hashing is popularly applied in all that, the construction of the concept behind Bitcoin. Also, I think most of you uses online file synchronization applications such as OneDrive or Dropbox, right? You can save files on the cloud, iCloud, all this. Most of you must be using one of these, whichever is your favorite. So when you want to save items in the cloud, you can access that from multiple computers or multiple machines, from phone, your laptop, from your desktop, from multiple places. And when like the application of hashing here is to sync your progress. So let's say you added a file on your laptop, which you edited from your desktop, and now you want to access it from your phone. So every time you are modifying or working on any file, when you save it, the sync operation needs to undergo, right? If you are modifying a file in your laptop and when you open it from your phone, you should be able to see the most recent version of that file. And hashing is used to detect if the version on a particular device is recent or not. So definitely, what else? Where else hashing is used? There are many applications of hashing. Other popular field where you would find many hashing concept is networks, where network router management, routing different packets, server distributed servers, they need to use hashing to see if the latest packets are transmitted, are received, did the packet transmission failed, does it needs to be retransmitted, many different applications in the domain of networking itself. So as you see, domain of networks, domain of memory management, like caching, the domain of database management, the domain of cryptography, security, right? Cryptography is nothing but the domain of data security. Compilers, like what not? This doesn't this involve includes the world of computer science, right? So hashing is used everywhere in computer science, basically. And now this should make you interested more about learning what is hashing, correct? So if you learn hashing, if you understand the concept of this module at its very core, you should be able to understand like its application in all these different domains. So whichever domain you enter in your future, in your further studies, you should, if the concept of hashing is clear to you, there should be many things in this related to these different areas where you can actually apply this concept of hashing and you can actually like solve real world problems. Okay, so in C++, we implement hashing by using hash tables. What are hash tables? Is nothing but it's a data structure, right? I'm just writing the acronym. It's a data structure that maintains set of items each with a unique key. So we can visualize this as a table where in this table you can store a set of items. These items can be something like item 1, item 2, item 3, and so on and so forth. The unique thing about hash table is each item is associated with a unique key. And whenever you want to access this item, you just look up by using this key. So in order to access the item, let's say if you have the hash table h1, then you just do h1 of k1 and you should be able to get item 1. So this hash table data structure, different operations that you can do in this data structure is definitely insert item, right? No, if any in any data structure, if you're not able to insert, then that data structure is waste because you want to basically populate your data structure with more and more items as you go on or initially. And in order to do that, you need to be able to insert items. So insert is a popular operation on hash table. Delete is definitely most of the data structure that we saw until now. We saw what's the cost of inserting a new item, what's the cost of deleting an item from that, and what's the cost of searching an item into that. So these are some of the major operations that we do on any data structure. Searching. And when you search an item in a hash table, you need to give key as an input. So you are searching an item that belongs to this particular key. So these are some of the basic operations. So every key is linked with an item, or in other words, we can say that every item has a unique key. And the cost of searching in hash table, what is it? That's the whole purpose of learning this new data structure, hashing, because we want to do search at the constant cost, big O of 1. So the in order to search any item in this data structure, because you already know the key, you directly do like ask for the put a query to the data structure using this key and you just get that item. That's a constant cost. So hashing or hash table, it brings us an ability to examine an arbitrary position in big O of 1 at constant cost. It gives us an ability to search any arbitrary item in a data structure at a constant cost. What we do is we allocate And a set of items or an array that has one position for every key. So every item is linked with a unique key, and every key has a unique position in this hash table data structure. So hash table data structure could be just a big array where you have different items stored in that array, and every item is associated with a unique key. What are key purposes? When you are doing, think if you are initializing such an array, then you definitely want to ensure that number of keys that you have in that number of keys that you want to insert in that array is less than equal to size of the array. So as we saw here in this graphical representation, oops, go back. Okay, as we saw here in this graphical representation, if this is your size of the array, you want that size of the array to be definitely much bigger, or at least bigger than the number of items you want to store in that array. So the remaining items, you can just say that those are null, right? You can initialize your array with 0 or with null, and then when there is an insert performed, then depending upon the hash function that you are using, which we'll soon see. So depending upon the hash function, you use the hash function to get the location of where this item needs to be stored in this big array. And then at that location, you insert this item. Every time you want to look it up, as soon as you give the key that, hey, this is the key I want to, the item which is linked with this key is what I want to find out, then using the hash function again, it will do a lookup into this table and it will say that, oh, okay, this key is related with this particular item. It will return that item. So these are different operations that we perform. So if it's an array, then if we are finding an item in that array, right? If a search is done on an array for a particular item, then what we need to know is array index. And this array index is computed from key. So when a user comes to the hash table data structure and says that, hey, I have this key and I want a value for this, whatever the item is attached to this key, then we take that key, and from that key, somehow we need to know what is the index of the array where this item is stored, right? If this is the array, then your index are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 elements in this, 11 elements stored in this array. And if the search is for, if this is a hash table 1, and if the query is get me the item that's associated with key 3 in H1, then somehow we should know that, okay, this item is stored at index 6, right? We need to be able to link the index of the array to the item to find the item. So this needs to be able to link that that's h of 6 that I want to return. And once you know that that's 6, then you can just return the item 3 that's linked with K3. So these are different operations that we want to perform on hash table. So what is the most simple approach to perform such a hashing? So the key thing that we are missing is how do we link key to the index, right? How do we link which key is stored at what index? Let's see, in the most simple world, one of the easiest approach is to just define your index is equal to key, right? Then in that case, you can have this big set of big array which you initialize, and initially you just say that all the elements in this array are initialized to null, right? This is null, not -1. It's a slant array. And then, because if it's an array by its own nature, you have index for all the items. And the simplest approach of maintaining such a hash table could be, say that your index is equal to key. So whenever a new item needs to be stored, so if you get an insert a key value or item pair, right? Key one, item one, if you get this as your command, then what do you go? You go to this array, and what you do is, using this rule over here, in this hash table H, you would insert this item at the location of key, at the index key one. So you would say that, okay, at this location, I store item one. So later, if you get other commands like delete key one, then you know which index to look for. Then this means you will pass a command which is delete or set the item whichever is at h of 1, because you know key 1 will be stored at index 1 from this rule. And you will say that, okay, set h of 1 equals to null. Or if you get a command like search key 1, again from this rule, you know that if it's a search command for key 1, I'll find the item that's associated with key 1 at index 1, and that's where you will do a search, or you look up what is h of 1 and return that. In this way, you can store multiple items, right? In this table, like item 5 will be stored here, item 7 will be stored here, and you can do these operation in this manner. So, well, if this in this way, if you can make hashing work, then we are done, right? Let's end this module over here. And why should we need to look anything further? Are there any drawbacks of this approach? What is the shortcoming of this approach, this simple approach? We love simple approach. They're easy to understand. They're easy to use. And if there are no drawbacks, let's just continue using them, right? Unless we have some drawbacks with this. What are the drawbacks with this approach, with the simple approach that we just designed using this rule? Think, think, think. This approach is also called as direct access table. What is the drawback of this direct access table approach? Where in this approach, we are storing items in an array indexed by key or with key. Okay, so by now I think many of you would have got your thoughts rolling on the drawbacks, and most of you would have come up with at least one drawback of it that would make this approach not so good to be called the world of hashing, right? Hashing has so many applications as we see, and something this simple, if it's usable in these many applications, well, that's a matter to think, that does it have any drawback or not? And most of you would have come up with at least one drawback. So there are two main loopholes, or two main drawback of this approach over here. The first drawback is if you are storing items in this fashion, if you are storing items in an array by indexing item by its key, then what happens when your keys are negative, or when your keys are not a whole number? So when your keys are something like 1.5, 9.668 minus 2, something like this, what do? You can't have an index that is minus 2, right, in an array. Or you can't have an index that is not a whole number, so you can't have an index that's 1.5. So this approach, this simplistic approach, won't work if your keys are either negative or they are not a whole number. We will soon look at how do we handle this drawback, and we will design more advanced approaches. But before that, what is the second most important drawback? Did anyone think that this approach, we are initializing this huge array, right? We even said that the size of this array needs to be greater, much greater than, where did we say that? The size of the array needs to be much greater than the number of keys that we want to store in this array. Right here, if there are 3 items that we are storing in this array, but we are initializing array with many other elements, with the potential of that it can store many other elements, so that if there are any future inserts, we don't want to miss that. So if there is a single key that is, let's say your key is equal to 5926001, then in order to store this single key, let's say in this hash table, you're storing just one key value pair. But if you use this rule, then you need to have an array that is of at least size this much, right? In order to store this key. So looking at this characteristics, its second, or one of the biggest drawback, is that this approach leads to a problem of gigantic memory hog. I like this term. So you are initializing something that's just going to be a gigantic memory hog, and you don't even know that you'll be using all that whole the whole amount of that initialized memory or not. So is this worth? Definitely not, right? So let's see, how do we go ahead and how do we solve each of these drawbacks? So in order to solve our first drawback, where let's see how we can tackle the first drawback, which is if we have the keys that are either negative or where those are something that is not a whole number, something that is a factor, the keys that are decimal fractions, then how do we store in the hash table? So in order to solve this problem, we can have another hash function. Let's call this as prehash. And the job of this, we can define such a function, right? And the job of this function is to map keys to non-negative integers. So if we can come up with such a function that does this, then well, if any key, let's say that this is our prehash function is f1, then whenever we have any key that comes in, first we pass it through this prehash function. So we compute the prehash for this key. If this key is originally a non-negative integer, right, then it remains the same. But if it is not a non-negative integer, then we get something else, let's say key of A. And now key of A is guaranteed to be a non-negative integer, right? So if we can come up with such a function where f of k is k if k is non-negative integer and otherwise it is something ka where ka belongs to non-negative integer otherwise, okay, something like this. So if you can come up with such a function, then such a prehash function, then our problem is solved. Now what could this function look like? You can have something like, so in theory, keys are finite and discrete, right? That's what you want. So we have many different options. Let's say that if the key that was given by the user is a string, let's say the key is ABC, then how you can design this function for such a key could be that if the key is string, then you find out ASCII value of each character of that key, right? Find the ASCII value of, let's say that the ASCII value is A1, A2, and A3. For A, B, and C, you find that ASCII value is integer, and then you add, it's a non-negative integer, and then you add this ASCII value. So you do A1 plus A2 plus A3. So sum of a non-negative integers is a non-negative integer. So whatever answer you get, which is A, should be a non-negative integer, and then that's it. So finding out an ASCII value of each character of the string, if your key is a string, and then adding ASCII value of each character of the string, that's your function in order to make this happen and solve this problem. What can be some of the other options? Your modulo operator, right, or absolute could be another way. So if your key is negative, then you just find, not modulo operator, absolute. If your key is negative, then you can find the absolute value of that key, and that will ensure that now this is non-negative. Or you can use the base operator. So if your key is integer, then you can find out the base of that. So base of a key of any integer is nothing but rounding the integer off to the whole number or non-negative, if your key is a fraction, then rounding the integer off to the integer that's smaller, to the digit that's smaller than that integer. So let's say if your fraction is 1.5, the base of 1.5 is nothing but 1. If your fraction is 46.25, the base of 46.25 is 46. So this could be your function, right? Finding the base. In the same way, finding the upper bound could be a function. If you are finding the upper bound or the top of that of a fraction, then the top of the fraction is rounding it up to the nearest in the forward direction. So the top of 1.5 is 2, top of 46.25 is 47. That this function will ensure that your fraction is converted to an integer, a non-negative integer. So you can have a function that's accumulation of all this, and then having this very nice function that identifies what's the pattern of your input key, and then accordingly applies whatever is required to that to ensure that the output is a non-negative integer. This will solve your problem, right? So if we do this, we are able to tackle this big drawback. And doing that is not much impractical. Once you give a thought and once you design such this function for all types of keys that user can input, and that's it. That's a one-time work. Okay. How do we resolve the second problem that we have over here? So now that we have solved the first problem, what about this? The big monster is here, right? Gigantic memory hog. Is there a way we can resolve that? Can we modify the simple approach of hashing in a way that when we insert our items, it doesn't have to be a gigantic memory hog? We don't need to initialize this array that's dramatically bigger than the number of items that we are storing into that. So what do we want is, let's say this is our key space. Right? In this key space, if we have different keys, K1, K2, K3, K4, K5, we want to reduce our key space in a way that we allocate memory only for the required amount of items. So if our whole key space is this square box, and if these are set of keys that actually exist in this data structure, then we don't want to allocate like the gigantic memory for storing the key space, but rather we want to have, still need to initialize some space, but we want to reduce that amount of space. So if there is a key, as we saw, which is something like 5904261, then you don't want to initialize an array of this size. Rather, you want to initialize, if you know that this is one and only one key that will be stored in this hash table. Hopefully that's not the case. Let's say that it's not just one key. Let's say that you have some X number of keys that needs to be stored in this table, and X is definitely greater than equal to 1. But out in this X key, one of the key is this, But in that case, you want to ensure that the amount of space that you are allocating to store these X keys is not much larger than X. So you want to reduce the space that you are using. You want to reduce universe U. Let's say that the key space is universe U of all keys down to a reasonable size. Let's say that the size is M for table. So if your key space is U, you want to find out, or you want to come up with some size M, and this M, you know, is definitely, M is smaller than U, much smaller than U, but you know that M is capable of accommodating all the keys that you have. So if you have X number of keys, then M is sufficient enough to store those X number of keys, whereas M is also much smaller than the universe of whole your key space. So M is not equal to the size of an array, which is equal to this very big number, and something smaller than that. So if we can come up with some solution to this aspect, or if we can come up with something that is able to reduce our universe U to this size M, then we solve the second big problem of simple approach. So how do we come up with this M? Any thoughts? Okay, so I would encourage to think, let's say if you came up with such a way of finding your M, what would be your biggest problem in that world where your M is much smaller than the universe of keys, but you know that M is sufficient enough to accommodate your keys that you have until now. But when more and more number of keys are inserted in this data structure, right? Because M is something that's constant, right? So what would be your biggest nightmare for such a solution? So if your M is constant, you know that M is good enough for number of keys that you have until now in your data structure, that's X. But if there are more inserts in this data structure, then what would happen? If we can solve that, so if we can come over our biggest nightmare in this approach, then probably you can just define M as some constant, right? If you have 5 elements in your data structure as of now, if your universal key space is of the order of 10 to the power 51 something, but then you can say that, okay, M equals to 15 is good enough because you have only 5 keys. You give some more space to insert more items into that, but that's it. But then when this data structure is used again and again, you don't know how many inserts are going to come, right? Just depending upon some some assumption that you are making that, okay, if I have used this data structure, I have observed the use of this data structure for 1 day, and 5 keys were inserted in 1 day. If this data structure is anticipated to be used for another day, like let's say for 2 days, then I would say that 15 is good enough size of your M. You are giving double the space of what? So even if the traffic that comes tomorrow is double than the traffic that came today, still your data structure would be able to manage it. But well, in real world, there is no guarantee. How much ever anticipations or predictions you do, there can always be something that happens that's worse, right? I think all of you have been through the situation where suddenly from nowhere, so many people show up at your party, and then you are like, how do I manage? So that's the situation over here. So if on the second day, if your traffic is way larger than the double, then what's the problem that happens over here if for with this constant M? Collision. Collision is your biggest nightmare. If you reduce the universe to a constant set, this constant set is definitely, according to you, good enough to accommodate the keys that this data structure might get, but not always things work according to your anticipations. And if it doesn't work, then collisions will happen. And collisions is, if we are able to come up with a way of how do we deal with collisions in this, then maybe we might be able to um, think of one step towards solving that big gigantic memory hog problem. So what is collision? Collision is a scenario where you reduced your universe of key space, which was dramatically large, to save the memory that you need to initialize to n. And when you reduced it, the function that you use to reduce this universe to the small m, that accommodated the keys that you already have, right? Let's say if you have 2 keys into that, it accommodated that. But later you got this new key. Let's say you got key 3. And if this key 3 also maps to the same index of another item, or the index where there already exists an item, then we call this scenario as collision. Same as when your car collides with another car. I hope none of your cars collides with anyone else's car ever, but that's the collision. So when this can happen, right, in what we are planning to do, we are planning to decide this finite set M that is smaller than you. So if you have your memory allocations equal to you, well, there'll be no collisions. But, and that's something like this simplistic approach, right? If we follow the simplistic approach where you map every key to an index ID, there is no collision. But this is not practical because then you need to initialize a big amount of memory, and that doesn't make sense. And if you want to be a bit stingy on the amount of memory you want to allocate towards this hash table, and you just don't want to go ahead and say that, okay, whole computer memory that I have, you can use it to just save this hash table. Then what would happen is as soon as you open any another program, it will just shut it down and you won't be able to open it because your whole memory is just dedicated to one single hash table. And none of you wants that to happen to your computers, right? You want to do multiple tasks. You will have your browser open. Now, most of you might have your browser open when you are watching to this module. You have this window open, the video open where you're watching this module. You have many other things open, maybe if it's a Mac, Finder open, Safari open, many other operations that's going on in parallel. And you don't want to just do only one hashing operation by your computer dedicated for hashing. So if you want to limit the amount of memory that this hash table is going to consume, then we might, because of this limitation, now because our M is a finite set, which is smaller than U, we might encounter this collision. And if we can solve, or if we can come up with the ways to resolve the collision, so we cannot avoid the collision. We want to allocate something smaller than the universe, right? If we do this, then we know that we will encounter a collision. But in case if the collision happens, then how do we resolve it? So let's take it like, let's say there are n number of cars in the universe. And if each car gets its own private road to go from any location, any source to any destination, then there'll be no collision, right? Wherever you want to go, each one of you get your own private road. But well, that's not practical. That cannot happen. Then imagine number of roads we'll have. Number of roads from any source to any destination is equal to number of cars. Oh my God, I don't want our world to look like that, full of roads. So in that case, then we have to share a common road. And now when multiple cars share a common road, then there are chances that collisions happen. We collide sometime with some another car, and we do have a protocol of how we resolve that collision. And until we have that protocol in place, then that's fine. We can use this shared resource. So in the same way, if we come up with a method to resolve the collision, so if collision, let's say collision, let's assume that collision happening is one of something that we can't avoid. But if it happens, then how do we resolve it? If we come up with that technique, then that's fine. Okay. So one way to resolve it is just say that if there is a collision, just say that, hey, there is a collision. And so sorry, we cannot insert this new key. So whenever if the K3 comes and K3 has, if you, once we look at the hash table, once we hash our K3, what's going on here in between is hashing, right? Hash function. So once we input, let's say our hash function is h. So once we find out h of K3, we we get the same index. Let's say this array has index 1, 2, 3, 4, 5, 6, 7. If we get K7, and we already know that this array has A of 1 is A1 and A of 7 is A2. We already know this, that this array A has these two items already stored in that. So in this case, if hash function of when we input K3 to our hash function and if it returns the same index 7, then we have the collision. And if we have the collision, we just say that, sorry, we cannot insert K3. This is one of the easiest way when you don't know how to do or how to resolve anything, just say that you can't resolve it, right? That's the easy approach to solve any problem. But definitely, this is not what we want to do. If this happens, then most of our applications can't use. If our hash table is following this rule, then I don't think we want our applications to use such a hash table, because in that case, every time collision happens, which we know that will surely happen in most of the cases, and then we just get the error to do that operation, right? So that's something like you want to do something using your computer, but you can't do, and you just keep getting an error. Sorry, you can't do this. Sorry, you can't do this. You don't want to be user of such a computer, right? It's frustrating. So this is not a good approach. How we can do something better, how we can accommodate such a request. One way, what we can do is chaining, right? We can have a linked list that's associated with every index. And if there are more than one item that's inserted to that index, so in this case, because we already have A2 over here, we can store the new key or the item that belongs to the new key in a new location. Let's say that new location is something. There we are storing this A3, that's the item that belongs to K3, and we are making a linked list from this index. Oh, that's not 7, it's 5. Sorry, my bad. Okay, so this is 5 over here. So we are storing this new item that has a collision with a previously stored item. We are not just saying that, oops, we can't, but rather we are making this provision where we are initializing a pointer from the index 5. And we are saying that, okay, from index 5 is storing A2 as well as it's storing A3. And so on. When new keys keep coming, you either, if there is a space, if there is null, right, then you can directly insert that key there. So if you get a new key K4, if K4 is mapped to A7, then if A7 is null until there, then you can directly store your A4 over here. But if you get something like K5, and if K5 by your hash function is mapped to something where the item is already there, like A of 1, then here you can again have a pointer, initialize a linked list, and then accommodate the item that's related with this new key that collided. That's A5, for example, and so on and so forth. You can keep on saving items in this process. So what's the biggest drawback, or what's the problem with this approach now? It's better than saying just no. So it's better than working on a computer that just keeps saying you, or keeps popping a dialog box or an error box saying that, sorry, you can't do this. Sorry, you can't do this. Sorry, this operation is not possible. But there is a problem. The problem is, we said hashing is so popular because it allows us to do a search with a constant cost. If you store your items in this manner, what is the worst case cost that would incur to search any item? Let's say if you have, somehow your hash function is not that good, or somehow the keys that the user gave are just like this one set, which is not that good, and it ended up in, rather than, although you have this size of m elements initialized, rather than using this m different elements, because of the type of the set of the keys that user gave, it ended up having this big long linked list, all colliding, and all just at single index. Let's say this is an array, and just at your this index, which is something, let's say 5, you had all the elements that are inserted there, like n elements inserted, collided, and gave this answer as 5 as your index, and then you ended up making this long linked list of n elements. So whenever you want to do a lookup to this hash table, when for a lookup, when you pass a key to the same hash function, it will give you an output. So when you pass something like search, each of this item could have some unique key, K5, K6, K7, K8, and you say that search K7, it will say you that, okay, K7 is stored at index 5 in this array or in this hash table. So you go to index 5, but now index 5 has this n elements that's stored within that. So you don't find your K7 right. Like there's no guarantee that you will find your K7 at your first most item in this linked list, right? So again, same as the complexity of linked list, in the same way, we'll have here the problem that we have here is nothing but your cost of search. It will increase in worst case. If this scenario happens, then that becomes big O of n. So we are deviating from our whole purpose of using hashing. And that's why this is not also a big solver. It's one of the way you can solve the collision, but it's not the most optimal way to solve the collision. So what else can we do? Think about it. And I want some of you to come up with a better approach. I know that you can come up and you can think of something better than this. Okay, I'm back. What are your thoughts? Hopefully, some of you came up with recurrent hashing. That's another technique of popularly solving the problem of collision. Okay. Also, sometimes popularly known as rehash. So what you do in this technique is once you hash a key, your hash function is edge. Once you hash a key, whatever value you get, that in this case, it's an index of an array. Let's say you got I1. If this index is colliding with some another element in your hash table that already exists, then what you do is you perform some mathematical operation. This could be, for example, it could be something like every time whenever you have a collision, what you do is you add the index of that element of what was the result of your hash function to the key itself. And then whatever result you get, you apply hash function to that. So definitely, because this is a new item compared to this item, so when you apply the same hash function to this new item, you will get a new result, right? Let's say this time you got I9. And you keep doing this until you finally find a place where you don't collide. So if you collide, you perform this operation. If you do not collide, then you just store. Go ahead and store that operation. And when you store, it's so in this type of hashing, you got to maintain a sense of counter of how many times you rehashed that value, right? Because think next time, definitely we want to, when you have such a hash function, such a hash table that's storing information in this fashion, then definitely later sometime you would have to do a search operation. And let's say that this search is for K1. And you know that in order to, first time you tried to store K1, you got index I1, but there was a collision at I1, and that's where you applied this phenomena of recurrent hashing. You added the original key to whatever was the result index of which that was the result of your hash function to that, and then you hashed that added value, and then you got a new index. And you did this once, and then I9, then you got this new index. This new index was empty, there was no collision, so you directly stored item there. So here we are not making any kind of linked list, but what we are doing is, when you have this hash table, you try to insert item once, and if there is another item that already exists there, then you do something, come up with some smart mathematical operation. So you do something and then you rehash this item again. So you say that, okay, this location is not available, but now I have come up with a way to find a new location. And let's say, for example, even if at this place, the new location, if this is something is stored, then you do some mathematical operation again, and then you rehash using that mathematical operation, and you find a new place again. And you never know, like how many times you have to do this for to find a place which is empty, and you keep doing it until you find a place that's empty in this hash table. Hopefully you don't have to do it many times, but whatever, how many ever number of times you did that, now when there is a search query, at that time you got to know that, because when the search for K1 happens, if for K1 you did rehash once, then first time when you apply, when the search operation for K1 arrives, what you will do is you will apply the same hash function that you have for K1, then you will end up at an index I1. But I1 is not a correct index, right? You have not stored your K1 at I1. Rather, you have stored your K1 at I9 because you rehashed. And you don't want to do the search again and again. Or even if you have to do the search again and again, how many times you have to do? How many times you have to trace back? You got to know. So first time you apply the hash function, you'll get I1, but I1 is not equal to I9, right? And I9 is the item that you are looking for, because K1 is linked with item A1, and item A1 is stored in this A of I9. So the item that's stored at I1 is not equal, oops, it's not equal to it's not equal to A1. A1 is an item that you're searching. So then what you do is you take this, now you know I1 anyways, after this applying the hash function for once. So you take the key, you already know the key, you take the key, you take the index that you found out, and then you apply the same mathematical function that you apply originally to store the keys. So then you get a new value, you apply h to this value again, you find out the new index, in this case it's I9, then you search if A of I9 is what you're looking for, right? You're looking for A1, that's your search. If it's equal to A1, you return that. If not, you keep on doing the same process again and again until you find that. So in this way, You don't have to search through a list, and your worst case cost is not big O of n, but still it may or may not be big O of 1, depending upon how fast you find that element, right? If the element is found at your first hash resolution itself, then that's good. Then your cost is big O of 1. But if it's not found, then how many times you have to do the rehash, that is what defines the number of the cost for the cost that would incur for this search operation. So your cost depends on number of rehash on an average that you have to do to find any element. And you don't know how many rehash you have to do for which particular element. So this is another option, but another option that is practically used in many applications to solve collision. But is there anything better that we can do? Well, there is straightforward ways of some another ways that you can apply. So rather than applying the rehash, right? Rather than applying the hash function again to some mathematical formula like addition that we did to the value again and again, you can have some simplistic operation like if you incur a collision, if you incur, if an item is stored over there and if you incur a collision while you want to insert a new item, then you can always keep on searching for a next possible empty place. So you can keep on increasing the area of the index till you find, let's say that there are some items stored. And so if you incur a collision over here, then you search the next index of that array. If there is an item there, you search the next. If there is an item there, you search the next, so on and so forth until you find something that's empty. And as soon as you find something that's empty, you store whatever the item that you want to store. So this K2, the item that's linked with K2 will be stored over here if this is the next possible empty space. Let's say that's A2. Again, the cost of a search operation in this approach depends upon the length of items that exist in a consecutive order, right? So if there are items that are already stored in this list, and most of these items, like the longest consecutive list of items is equal to m is equal, let's use some another variable because m is the size of our hash table we used for that. Let's say this is p. If the longest consecutive list of items that's stored in the hash table is equal to p, then your worst case costs in which you end up at the top, your key that you want to insert ends up at the top of this longest possible consecutive item list. And then you have to go through a whole this list next until you complete that. There might be some another items stored here and there in this list, right? AIs, AJs. So if your key happens to be here, then the next item is empty, no problem, just one operation. But this is the longest consecutive list. So if your key happens to be inserted at this index at the top of the consecutive list, then you have to do the operation that's equivalent to the longest consecutive list, which is P, and that will dominate your cost of search. In the same way, rather than storing the items in next fashion, you could have thought of some another ways that, let's say, you can store items at, you can do this jump. Here you are jumping at the step size of 1, right? You can do the jump in a binomial fashion. You can do a jump where you first time you jump by 1. If you find an item there, then second time you jump by, first time you jump by 1. If you find an item there, then second time you jump by 2. And again, if you find an item there, The third time you can jump by 4. If you find an item there, then next time you jump by 8, and you keep on increasing your jump size, assuming that in that way you will find an empty slot in a faster way. In all this approach, the cost of search depends upon how you, the strategy that you frame to find this empty slot. But these approaches do ensure us that we will be able to resolve our collision problem. Okay, so now we did discuss some of the approaches in which we can solve the collision, though there is definitely, this world is not perfect. And because we are not in this perfectly well restrained world, so we come up with solutions. The solutions might not be the best of the best, but these are the solutions that works. So those are some of the simplistic techniques in which you can resolve collision. If you are able to resolve collision, then you can resolve the problem of gigantic memory initialization of hashing, simple approach of hashing. There are definitely more advanced solution which we won't be entering into in the domain of this course in hashing. They could be like an entirely whole course on hashing. In fact, if you are interested in hashing, to learn more about hashing, I do recommend you to take some of the security cryptography related courses of our curriculum, and those jump more into detail about other more advanced approaches. But what the main purpose of discussing the concept over here is to introduce you to hashing, to introduce you the problems that occurs in different approaches for hashing, and how is practically those problems solved. So these are some of the very basic techniques that we are discussing over here, but definitely there are much more advanced technique, and you are all free in the world to either Google about those advanced techniques or take some further courses like security related courses that dives more into those advanced techniques. So our goal is not to discuss or not to come up with the best possible solution, but our goal is to give you an exposure to how the solution can happen. Now, we already discussed the purpose of hashing, the motivation behind hashing, the applications of hashing. We discussed a simplistic approach towards hashing, and then we discussed the problems that this simplistic approach has, two main problems. We discussed different ways of solving this two main problems. One of different ways of resolving the collision, which was a problem that encountered when we want to solve the problem of huge memory initialization. So what's next? Hash function. Many of you might have that at your top of your head. All through now, in most of this, we kept on talking, or we kept on saying again and again about this magical hash function, right? We use the hash function and then we get this index I. We use the hash function h and we get something where we want to store that element. What is this hash function? Let's look into that further. Let's use purple. Okay, so we will look into some of the simple hash functions. Again, as I said, these are not the best hash functions that's used in most of the practical applications, but this is your first step to know about the world of hash functions. So let's look into some of the simple hash functions. So the purpose of your hash function over here is to take some item as an input, right? And then find out at what place this item in this hash table can be located, right? So if your hash table is stored in the form of array, then the purpose of your hash function is nothing but to take key as an input and to give you index of that array where the item that's linked with this key is stored. So that's something that we want to do. Now, along with this functionality, we know that from the discussions that we did until now, we know that we want this hash function to give us the index in the range that is way smaller than the universe of key space, right? This range, we have been talking about M. So if your universe is U, whatever hash function you are using, that hash function is the one that's going to map your items to a particular location in your memory. And you want these locations or these index to be given to you in a way that the globe of index that is a result of this hash function always falls in a set M, and where you know that M is almost equal, or let's say that if you have n elements in your item, then your M is almost equal to n or just a bit greater than n, but definitely it's way smaller than the universe of key space. So that's the purpose of hash function again. How do we come up with such a hash function? Can anybody think of what could be one of the simplistic function that can serve the purpose? One of the simplistic function is nothing but modulo operator, or we can say as h of k is equal to k mod m, where k is your key, m is whatever size of the reduced size of the universe that you desire, right? If the universe is what we took some huge number, we can take some another huge number. If the universe is 10 to the power 45, your m is way smaller than the universe, so it's way smaller than that 10 to the power 45. Maybe your m is 10 to the power 2, and your n is yeah, definite smaller or equal to 10 to the power 2. So that's your m. Your k is the key that you are trying to insert, and the simplistic hash function could be just the modulo operator. Now, how does this work? So let's say you got this huge big key, which we said in this. So let's say you got this huge big key that you want to insert. And let's say the m that you desire is 15, as we took in the example over here. Then you divide this number by 15, right? Divide this number by 15. And whatever is your reminder, that's the modulo operator. It gives you the reminder. Whatever is your reminder when you divide this number by 15, definitely that reminder is going to be lesser than equal to 15, right? Your reminder. All of you know how to perform division, and all of you have a calculator on your phones. So I should not, when you perform the calculation, if you perform division on your phone, then you will not get the reminder, but if you have an advanced calculator with a modulo operator on that, then you can find the reminder of this, and that reminder is definitely less than 15. If you are not sure why, then probably you got to revise your maths a bit. But and because of this mathematical property, that reminder is definitely less than 15. So whatever index we get as an output of this hash function, we know that it's definitely in the range of less than equal to m, right? And we know that that's a single item. So there can be no different m there can be no different k that has different m. So you cannot store the same item at multiple index, right? So once you give an item to a function, if you get one index as a response, and second time when you given the same item to that function, you get another index as a response, then that's not a good hash function, because you will definitely perform operations like search to this hash table. And whenever you want to perform a search, then you want to get the index as the same every time you do. And this function, modulo function, satisfies that constraint too. So this could be a simplistic hash function. What's the problem with this hash function? The biggest problem with this hash function is collision again. So it depends upon how smartly you select your M and what is your K. So the badness, or what's bad with this hash function, that's the just using modulo as your hash function, is that when K has some common factors with M, such as, for example, if K and M both are even, right? Then see what happens, right? If K and M both are even, they have many common factors because both are even. And because of that, the number of collisions that you have will be dramatically higher. And as you know, that collision resolution techniques are not that cost friendly to our search operations, as we have seen in this collision resolution techniques that we saw earlier. They are not much cost friendly, so you want to limit the number of collisions that you have, and your choice of using your hash function is one of the key parameter that decides that. So this is simple hash function which works, but it doesn't work much well because of number of collisions that may happen. But we can make some smart choices to depending on we can make some smart choices to select our M. K is something that user is giving, so we can't make any choice for our K. But if we select our M smartly, then we can avoid like having a lot of collision. And one of the good way of selecting a better M would be choose M as a prime number. In this way, you can ensure that it doesn't incur a problem of having common factors with your K. There are, if you refer to textbooks, one of the good choice I remember of M that many people suggest in many literature is something like root of 5 minus 1 by 2, some weird number like this. And then you can ensure that it has a least common factor with any type of keys that you get. It could be a prime number, it could be something like this, and that would resolve your problem of having more number of collision. You cannot guarantee that there are no collisions, but number of collisions that you have might be minimized depending on the Number of collisions you have depends on the keys that user gives or the keys that are inserted in the hash table. So this is one of the hash function that we can use. Let's discuss a bit more complex hash function as well. So let's discuss this another hash function that's popularly. So the first hash function where we use modulo operator, we use division method, right? Because we divided k with m and then we took the remainder. So if we can use the division method to design our hash function, then definitely we can also use multiplication method. To define our hash function. Now, this hash function is going to be a bit mathematically complex, and the real hash functions that we use in practical applications while we use hash tables, they are very mathematically complex. So, and that's what gives us the better hashing performance, right? As we saw that we don't want the hash table to occupy a lot of our memory, and then if you want to reduce, if you don't want to allocate the space equal to the universe, then you have to come up with a small subset of memory that you allocate of the size equal to m. Whatever this m is, you will have collision inside that. And one of the way to limit these collisions is to come up with a smartly defined hash function. So hash function is something that is the at most important thing if you want to keep the cost of hashing as constant. And that's where the hash functions are way complicated than what we are discussing over here. But these are some of the simple ones. So now don't panic with this mathematical operation of multiplication hash function. That is nothing but a multiplied by k mod of 2 to the power w. Don't panic, I said the disclaimer, with a shift applied of w minus r. That's it, very simple. This hash function is pretty simple, right? Let's break it down to understand what we are doing in this hash function. So here, a is nothing but an integer. K is your key. So this is a hash function that you're applying to the key. This is a right shift operator, a shift right operator. And W is the length of the character of your computer. So it's the word length of the computer. This word length could be, so let's say if the computer is W-bit machine, then the word length is that W. Okay, so we apply this complicated mathematical operation. Let's see if let's take an example and why we are applying this, like why this is a much better hash function than just a simple modulo operator. To understand that, let's see what's actually happening when we apply this hash function to any key that's given. So let's say that our key is our machine is 6 bits. This must be a very basic computer, a 6-bit word length machine. These are one of those early day computers. If you have visited to a computer science museum, then if they have those early days computer which look like a punching machine, so it printed like a long roll of paper with holes punched out, and the length of that, the breadth of that paper is what it's the word size, and maybe even those were better than the 6 bits. So 6-bit machine is really primitive, but for our example, it suffice. So let's say that this is your 6-bit machine, and it's just like a is some constant. So let's say this is your a. When your k comes, k could be anything, right? Your word length is 6-bit. So at max k can be 6-bit. Let's say your k is 6-bit. So what you are doing here is you are multiplying, right? So you're multiplying a with k. So how would this multiplication look like? So if your a is this, for example, 0, 0, 1, 0, 1, 1, if that's your a, then it would look like having, when you perform this multiplication, because 1 exists at this location, at this location, and this location. So it would look like having k at this location, at this location, like, right? That's how you perform multiplication. I'm just doing basic math. And then at this location. So you'll have, for zeros, if you multiply anything with 0, it's 0. So we don't have to consider that. But at this 3 location, because these are ones, you will have this. And if you add these all, right, when you perform an addition of all these bits at these locations, you will get the multiplication answer, whatever that a multiplied by k is. Now, the size of this multiplication answer that you get is nothing but this plus this, right? So if your key is of W bit, if your A is W bit, then this is going to be 2W. The length of your multiplication answer is going to be 2W. Now, in this, if you look at this word length, this word, the answer of multiplication, which is of size 2W, where do you think is the most mashup of everything going on? Which region is that? So imagine hashing to be on your stove, in your pan, taking all the leftover vegetables from your refrigerator because you don't know what to cook. You just take everything and then you just mix everything up, and that's it. You just season it with salt and pepper and have it. So such a dish where you mix everything up in a most homogeneous way, that's hashing. Where in this word of length 2W, where is such mashup of everything happening? In the center, right? This is the region where everything is getting mixed up, and you get like the most mixed up. The more you mix, the more tastier it is. In the same way, this is the region where the most randomized outcome is coming, is is there. So this is your prime thing that you want to get. Now, how do we get that? So this mathematical operation is about getting that most prime region out of this multiplication operation. What you are doing is you are applying modulo of 2 to the power w. So when you apply this modulo operator of 2 to the power w, then you take, so what, when you apply this piece of operation, then what you do is you just take the right part of this 2W word length. So that's the total word length is 2W. You cut it down into half, and you go and take the rightmost half of this one, that's applying rightmost W length words. That's when you apply modulo operator, right? The remainder you get, and the remainder in this case is nothing but the rightmost W length word. So mod something, this result mod to the power W will give you, or that's nothing but take the right W size word Now, once you have the one that's marked in red, once you have this right W size word, then what you are doing is you are right shifting the word with W minus R characters. So your R is nothing but this region. This length of word is your R, and you are right shifting this word. So when you right shift this word, you delete things from end, right? That's how you right shift. And when you right shift any word in computer, then you move the word towards your right, and that's way, depending upon the character that you are right shifting, you remove. So the region in purple is nothing but R bits. This whole is W bits. So this is W minus R, and you are right shifting your whole W length word with W minus R characters. So this mathematical operation over here says that you are chopping off W minus R characters at the tail of this word. So when you do this, you get this R words that are the result of the most mixed up and well prepared or well randomized um, character. And that's how you like, that's why this hash function is better, because you are mixing and doing some more thing than just a simple modulo operator. Your R, okay, we talked about R, we talked about removing R digits, but nobody asked question that what is R? R is nothing but, I forgot to mention, R is nothing but if M is the size of your table that you want, then R is nothing but 2 to the power R. So R is inverse of M. So this is the relation between your size, the desired size of the table, that's M, and R. So R is nothing but this. So this is your mathematical method of finding hash function, where for any key, you apply the same function, you get the location of where to store in that array of size M. And when you want to search, you again apply the same function, you know where the item was searched, where the item was stored, at which index, and you pull the item from there. This function, because it's more better than modulo function, it has less probability of collision, and that's why it's a better hash function. And this ensures that if there are less collision, then it ensures that your cost of search is, most of the time, it remains big of 1. There are more advanced hash functions. So if you are really interested in learning more about hash function, then you can try to break this hash function down and understand that. This is very similar to multiplicative method. This hash function is called universal hash function or universal hashing. What this hash function is an h of k, where h of k is equal to a multiplied by k, same as before, plus b, where b is another constant, right? There, a and b are random numbers, mod p, where p is nothing but a prime number, mod m. M is the desired size of your hash table that you want. So p is prime number, a and b are random numbers between 0, it could be anything between 0 and p minus 1, where p is this prime number. And for this hash function, where your universe size is u, you also ensure, like, how do you select this prime number is if you have to get a prime number that's considerably larger than your universe size. But this is okay. We know how to find prime numbers, and we know how to find really big prime numbers today, right? We are advanced in our computation that much. And this is just one time work. So once you find that really big prime number that's bigger than, let's say, not much bigger, but bigger, that's surely bigger than the size of the universe, you are not allocating the memory space for this much space in the memory for this much amount, but rather you are just using that number to compute your hash function, and finding that number is just a one-time operation. So finding a really big prime number is not a problem in our today's world. You find that, you ensure that that really big prime number is bigger than the size of your universe. Once you have that, then you apply that to this mathematical function where this is just a really big prime number, so just a number, and a and b are just the random constant, anything between 0 and p minus 1. And this function is one of the popularly used hash function. Why is it popular? Is because for worst case, keys that's k1 not equal to k2, your probability of h of k1, right? When your keys are not, for two different keys, the probability of their hash function being the same, so that's nothing but the probability of collision, is equal to h of k2. This probability of collision is equal to just 1 by m. What is the probability over here for? The probability is over the random numbers that you are picking, right? That's why it's the probability, because depending on different random numbers you pick, it's a probability function that you have, and the probabilities of this probability function depends on your random number selection of a and b. But so the probability of having a collision if you use universal hashing is very small. It's just 1 over n. So larger the m, smaller the probability of collision, right? Quite a natural relation, because you can imagine the more big m you have, when you get more number of keys, then you can accommodate those keys at various locations of this bigger m-sized array, and then the probability of collision is less. So because of this very fine property, this complex hash function over here is something that's popularly used. That's it. We won't be discussing any more hash functions. And if you are interested, again, this module of hashing is mainly to give you an introduction about hash table data structure, what operations you can do with that, and to walk you through some of the basic concept of hashing. And if you're more interested, please take the advanced courses of security that dives more deep into the hashing concept. So now that you know what is hash function, you know what are the key problems with hashing, you know what are the advantages of using hashing and where all it is used, why it is used, these all concepts. Finally, let's walk through an whole example, and let's use one of the technique that we learned. Let's use chaining because it's most common technique. So let's walk through the process of hashing and taking an example and using chaining. So let's say that our universe of keys, or let's say that all the keys that we have, our key space, not the universe, has these keys popping out numbers that comes out of my head. These numbers need not be sorted. They are just some numbers to represent our key space. Okay, my tablet, my iPad's breath is over, so let's take this much. Let's say that we are using a simplistic hash function, which is h of k is equal to k mod 9 modulo operator, where our 9 is the size of the desired hash table. So our 9 is equal to m, right? In everything that we studied. Let's write this with a different color. So 9 is m. And we want to store, when we apply this hash function for this key space, what are the index that we will get for this hash function? What we are doing is taking each key, 5 mod 9 is 5 because it's smaller than 9, 28 mod 9. 28 mod 9 because it's just 1 over 27. 27 is a factor of 9. 9 is a factor of 27. So it's 1 because it's just 1 more, 28. So the remainder will be 1. In the same way, let me do these things in my mind. 19 mod 9. 1 again, 3. This will be 2, 33 mod 9, 6, because 27 is the factor. 12 mod 9, 3. 9 ones are 9. 17 mod 9, 8. 9 ones are 9. 10 mod 9, 1. Okay, so these are your index, right? So when you have this hash table of size m, which is 9, you have 9 elements, 0, 1, 2, 3, 4, 5, 6, 7, 8. We started from 0, so there are 9 elements. And in order to store this key space, you will, if let's assume that we are using chaining. What you will do is store at that index. So we'll store 5 over here. Then when 28 comes, we'll store over here. When 19 comes, because there is a collision and we are using chaining to resolve collision, we'll store 19 over here. When 15 comes, that's empty. So we'll store, oops, need to plug in the charging for my tablet. Hold on, let me do that because I don't want this to get off. Okay. Where were we? We inserted, did we insert 15? No, we were inserting 15. And then 20 at 2, 33 at 6, 12, because there is a collision at an index 3. So using chaining, we'll make a linked list and store 3. 17 at 8, 10 at 1. Now there is a collision at this, so we store 1 more. So this is how this hash table will be constructed. And now with this example, I think the concept of hashing should be crystal clear to all of you. The challenges of hashing should also be clear. Hash functions, if you can decode the mathematically what's going on in this universal hashing function, similar to as what we did over here. And if you understood well what we did over here in this multiplication method, how hash functions are designed should be clear. as well as definitely where all you will come across hashing in future, or where all you can apply hashing in future. That should also be clear. So that's it. This concludes our module on hashing. And I wish that all of you enjoyed it and learned something new from this module. If you have any questions in any concepts that we discussed in this module, then please email your questions to me. And you know the drill. I'll get back to you soon, either by email or we'll set up a Zoom meeting to resolve your questions. Okay, bye-bye.